Hey guys, in this video I'm going to explain the second logic game from PrepTest 70, which is the October 2013 LSAT. This logic game is a selection game, also known as in and out. It's a type of grouping game, and we know this because we're choosing employees for a team out of a list of 8, and we're choosing at least 4 to be in. So I've listed out the 8 variables here, M, O, P, S, T, W, Y, Z, and I've also laid out the rules and connected them, and I'll explain how I connected them as we go forward. We know that if M is in, both O and P must be out, so here I have M in requiring O out and P out. Then I also wrote down the contrapositive. If either O or P is in, then M must be out. The next rule involves S, P, and T, so we can link that with the P that we already have on the bottom diagram here, and the negative P we have on the top diagram here. So S requires P, and S also requires T, so I've linked those with the same P that I used for the original first rule. It's contrapositive. On the other diagram, if P is out, then S must be out. Also, if T is out, then S must be out. So either P or T being out requires S to be out as well. Then the final rule, if W is in, then M and Y must be in. So I reused the same M that appeared in the first rule. Then the contrapositive, if either M or Y is out, then W must be out as well. Then finally we have the variable Z here, and there are no rules about Z, so it's a floater, it's an open-ended variable, could be either in or out no matter what happens regarding the other variables. So I've just laid it on the side there to remind us of its existence. And that's our initial setup for the game. So now we're ready to solve our first question, question number 8, which is a typical orientation question. So we can simply take one rule at a time and apply, that rule to all 5 choices, checking for violations. So to start with, we know that if M is in, both O and P must be out. So any choice containing M and O or M and P is automatically wrong. That gets rid of choice A for us, since A mentions M but also mentions S. That's unacceptable, so for that reason it's gone. The other choices don't violate that rule, so we'll move forward. We know that if S is in, we have to have both P and T. So scanning through the choices here that remain, we see that C and D both mention S, yet C only has P, does not have T, so that's wrong. And looking at D, has S, does not have P, so that's wrong as well. E is okay though. Now we'll go to the final rule. If W is in, both M and Y must be in. So checking, B doesn't mention W, but E does. E has W, does not have M, so E is bad, leaving B by elimination for question number 8. Next, number 9, we're looking for a pair of employees who cannot be together. So we're essentially looking for a conflict here, a situation where one variable in requires another variable to be out. So we'll just scan through the choices here. M and T do not have that kind of relationship. M in does not require T out, and T in does not require anything at all, so A is gone. Looking at B, O and Y in does not impact anything at all, so that's eliminated as well, and you can also see that O in does not impact Y. Looking at C, P, and Z, Z is always a floater, it's always on the side, there are no rules regarding it. So for that reason, P and Z don't conflict. Z doesn't conflict with anything, so C is gone. Looking at D, S, and W, S in requires W out, and W in requires S out. So yes, S and W do conflict. So for that reason, yes, D is a pair of variables where we cannot have both in. I will take a quick look at E though, W and Y. W in actually requires Y in, so they certainly don't conflict, and E is gone, leaving D for number 9. Next, number 10, if Y is out, then any of the following could be in except. So I laid out here a little in-out table. We know that y out requires w out on the bottom diagram here, so I put both of those out. Then we have in MOPSTZ. Now I'm not saying all those 6 will be in, I'm just saying that's the pool of variables that remain to potentially be in. Now of course there are conflicts here. So I would look for which variable conflicts with the greatest number of others. That way I can see which one would be difficult to have in, so that one would likely be out. So we know that if we have M, we're going to lose OP and S. M conflicts with the greatest number of other variables. If you have M, you lose 3. Same with W, by the way, but W is already out. So if we had M, could we still make it to our minimum of 4, which, remember, the original setup of this game requires. The original scenario says we got to have at least 4 in. So M in, you lose OP and S. That would mean you only have 3. You have M, T, and Z to be the 3 that are in, but that's not 4. That's only reaching 3. So M is our problem variable. So for that reason, M is the one that could not be in, and so E is our answer as a result. Next, number 11. If P is out, what could be true? So P out requires S out according to the diagram, so I listed both of those out. That leaves the remaining variables M, O, T, W, Y, and Z to potentially be in. Again, I'm not saying that all 6 of these are in, just that these are the variables that remain to potentially be in. So looking at this, they're asking us what could be true. So automatically, you can eliminate A, B, and C because they all say that you do not have M. But no choice mentioning M could ever work because if you lose M, you're also going to lose W. And then you would only have 3 variables left. So let's see what happens if you do that. If you lose M, you lose W, you have O, T, Y, and Z here. And A, B, and C are all saying that you lose M and you lose one of O, T, and Z as well. So if you lose O, you have T, Y, Z remaining. That's only 3. If you lose T, you have only O, Y, Z remaining. If you lose Z, you have only O, T, Y. So regardless, you're only going to end up with 3, and we need to have at least 4. So for that reason, A, B, and C are all gone. Now let's take a look at D and E. D says neither O nor T. If you lose both O and T, you're going to have M, W, Y, Z. Works out perfectly fine. None of M, W, Y, or Z conflict with each other, so D is actually our answer for number 11. I will take a quick look at number 12, though. 12 says neither O nor Y. So if we got rid of both O and Y, we have M, T, W, Z remaining. That doesn't work, though, because Y out requires W out as well, so we'd have to lose W also, leaving only M, T, and Z, which is only 3, and we've got to have at least 4, and as always, so E's gone as well, leaving D for number 11. Finally, number 12, we're looking for a pairing of employees where we got to have at least one of them in at all times. In other words, where we cannot lack both of them. So I'd start by looking at the 2 chains here and looking to see which of those chains has, if anywhere, has a negative followed by a positive relationship where one variable being out forces another variable to be in. However, we don't see anything like that on these chains here. We only see positive variables followed by negative variables, which, as you know, represents a conflict. Or we see positive positive or negative negative, which isn't useful here either. So I would start here by looking back at previous valid scenarios, and we have that in the previous question, number 11, choice D, where we lacked P, S, O, and T. So using that information, we can eliminate both A and C right away because those pairings are part of the P, S, O, T list from what we had out in 11 choice D. So now I'd move forward on this question by looking at the remaining choices, B, D, and E. So starting with B, O, and W, could we ever lack both of those and still have a working scenario? Yes, we can. We could have, for example, S, P, T, and Z. Works out perfectly fine. Lacks O, lacks W, so we do not have to have at least one of those in, so B is gone. Then looking at D, T, and Y. Could that work? If we had T and Y out, could we still reach 4 in? We wouldn't be able to, because let's say we try to have a scenario involving O. If we have O, let's say we try to have a scenario involving, let's say, S. If we have S, we're going to have P and T as well, but we can't have T. It's not going to work. So if we try to avoid that, we have like T, O, Z. We only have 3. We'd have to have something like Y. But again, we're not allowed to have Y. If we go on the other diagram and look at W, if we have W, we're going to have M and Y. If we try to just have M, and then we have Z, that's only 2. So no matter what, we cannot avoid having one of T or Y. So D is our answer for 12. I'll take a quick look at E though, Y and Z. If we lacked both Y and Z, not a problem. We're going to lack Y, W, and Z. But we could still have S, P, O, S, P, T, and O works out perfectly fine. Those 4 are good. And we got to avoid having Y and Z, so E is gone as well, leaving D.